Okay, hello everyone. We are meant to hear the bell, but we haven't heard anything so far, so let's start. Thanks for coming to this symposium on biotic interchanges across taxa through molecular and fossil data. It's something that Alex Skills here in the front seat and me thought some time ago. And yeah, it's happening now. Well, I'm Octavio Jimenez-Robles, and I'm going to show you a bit of the project that I've been carrying out at the Australian National University and the École Normale Supérieure in Paris, in France. So, also, I would like to start acknowledging that the land in which we gather is the traditional territory of the Kanyenke Hakka, which has been a place which has served as a meeting and exchange site amongst nations, both from territories around and also from overseas territories, which actually goes quite in the line of what we are going to talk about in this symposium, because we will be talking about residents and newcomers, which, well, by the way, when I talk to people that I'm working on biotic interchanges, I realize that many people, even in our community, is not aware of what they are. So I'll just define them briefly. So basically, biotic interchanges are exchange of organisms between different biotas. The first, or one of the first people that started to realize about this phenomena is Wallace, when he started to realize there were regional differences between faunas. And for example, in the famous region of the Wallace line, he realized that there was this continuum in the biotas, which very different taxa across this particular boundary that we know as the Wallace line. And he realized that this barrier wasn't actually completely unpermeable. It was permeable. There were taxa that could go, that could cross it. Well, if you are interested about this topic, in the next talk, Audrey will talk about it. And also, I suggest you to read this paper that Alex Skills led last year that was published in Science. Also, another of the biotic interchanges that Wallace already pointed was also in the Americas, which later was further studied by Simpson. This has the study of this system has contributed undoubtedly to the development of biogeography and even to the development of evolutionary theories. We will have a couple of talks about the Great American Biotic Interchange, also in this symposium, by Katherine Magoulick and Kate Pino. Well, one of the most striking things that happens with biotic interchanges is that there seems to be asymmetry. And so this asymmetry can be reflected in the different origin of the lineages that composes each biota, different dispersal events, different amount of dispersal events between these biotas, or even it could happen that there would be different diversification rates. About this last topic, Nathan Masset will give also a talk at the end of our symposium. And now I'll show you a bit of what I've been doing. It's just a bit, so I'm happy to talk more later because I'm very passionate about this topic, and I will be just showing something actually quite modest. So, yeah, so as I said, one of the most interesting aspects of biotic interchanges is the asymmetry. So this asymmetry, we could hypothesize that can be due just simply by different sizes in the species pools of the original biotas, which potentially, yeah, it could be correlated to the area of the emerged land masses. Well, this is just talking about terrestrial environments. Of course, biotic interchanges could happen also in the marine environment when different sea basins join. And also the timing and intensity of this interchange probably is regulated by distance. It's quite straightforward, but actually there hasn't been much testing at the level I wanted to do it. So I want to focus in the Cenozoic period, because I mean obviously at the beginning of the Cenozoic was a big turnover of the communities, and during the Cenozoic we have a very interesting scenario due to all the tectonic plate movements in which different land masses started, well, different land masses that came from what was Pangaea, that was split in Laurasia and Gondwana, then it kept splitting, and it's actually during the Cenozoic where all these fragments that had been with biotas evolving in isolation start colliding. In some cases, even faunas that were split at the beginning of the split of Pangaea, which I find it fascinating. So as hypothesis, well, as I mentioned before, distances between the land masses and the size of them should drive the intensity of these interchanges. And we expect to have signs of asymmetry in the number of dispersal events. If we consider dispersal rates, which should be corrected by the species pools, perhaps there shouldn't be asymmetry in those. But so, yeah, to do that, I used some plate tectonic models, which allow me to recognize the different shapes of the land masses and the distances between them. Oh no, I'm going backwards. And yeah, so with this model, we can track through time how the landscape has changed during this time. So I decided to look at these 10 different areas because we can see them consistently during this time. There are some of them, like Wallacea, that are more recent than the others because it emerged from the sea while the Sahul was pushing against Eurasia. And also, well, the Caribbean, it was already at the beginning of the Cenozoic, but it's also more recent than other of the areas as well. So I ran ancestral biographic reconstruction analysis using the phylogeny of squamates of Tonini and the distribution data from the IUCN and the Global Assessment of Reptile Distributions. Sorry, I'm getting backwards. So once we get the probabilities of the nodes of all ranges, we get these stochastic maps, like these ones, in which we represent the different possible stories. And there we can track dispersal events. So in this case, I was counting how many dispersal events happen in each 5 million year time beam. And in each of these time beams, I could also calculate some dispersal rates by dividing the number of dispersal events by the sum of the branch lengths corresponding to each source area. And then, although I fit this analysis without informing the method by distances and areas, then I wanted to see what we were inferring naively, how was correlated with these distances I was measuring in the plate tectonic model. So here we have some of the stochastic maps. Well, you can see a lot of transitions, especially during the Cenozoic. Obviously, before the Cenozoic, we don't have many branches. And if we look at the dispersal events, we see that in general we have a big bias towards more recent times. You can see in all cases it increases. That we are aware that that's a problem inherent to the phylogenies, because we are missing information on all the extinct taxa. And we can see some asymmetry in this. For example, this is Eurasia against India. We can see there's more Eurasian taxa going to India than from India to Eurasia. And similar cases in the other pairwise combinations. These are the rates which we can see there is variation. And for example, if we look at the same example of India against Eurasia, we see that in general we are recovering higher rates of dispersal. Yes. So if we look at the correlations, we find that dispersal events have an effect of time that is negative in this case, because we have less dispersal events as we go back in time. And then, well, also we see that distance has a strong effect, which is negative, which is according to our expectations. But then if we look at the dispersal rates, we don't find such a strong effect of distances. And actually we find a positive effect of time, which is quite striking. So I think I will wrap up here. So I will skip this. So yeah, we can see that in fact different species pool sizes could be the main cause of asymmetry, although there could be another drivers, which some of them I didn't include, like environmental similarity, which is something we can see in the study we did with Alex. Also that dispersal rates, according to this, could be asymmetrical. Oops, that's for us, no? And yeah, and also to point out there is some issues with the approach because we are missing extinct lineages, and actually the DEC model, which I use for the reconstruction, assumes that dispersal rates are constant between areas and through time. We can discuss more about this because, yeah, it's a lot to tell there. And yeah, I would like to thank the Moritz Lab and the Morlon Lab, also the funding I got for doing this research from the Marie Curie program, and also funding that covered my registration from the Society of the Study of Evolution. We don't have time for questions, so we will proceed with our next speaker, Audrey, that comes from the Australian National University. Audrey, you can come.
Hi, everyone. My name is Audrey. Hold on, I'm just gonna... I do come from the other part of the world and hemisphere, quite far away from here. And today I'll be talking to you about one of the biotic interchange that Octavio talked about, which is the Sunda-Sahul biotic interchange, specifically on birds. But this talk has a bit of a focus on islands, And that's because islands are incredible places. We like to go, well, they're great places to go on holidays. This is an island from my home country. This is where my mom is from, in Indonesia. And an interesting part about islands that we like to talk about is how do they get their biodiversity. Most biodiversity from islands come from continents. The movement of a species towards an island is just colonization, but we also can consider it as downstream colonization. And this is, of course, explained by the theory of island biogeography, where islands usually receive species that are from areas closer to them, so the effect of distance, but also the area of the island itself. However, when a taxa reaches an island, of course, it can then diversify. And then after it diversifies into other forms of species, there's also the possibility that this species will move from island back to the continent. And this is what we know as upstream colonization. This used to be considered a rare event because of reasons. There's a lot of different reasons. One of them is, of course, island syndrome, the lack of competitive ability for island species. But actually, recently, this has been a different change that actually maybe upstream colonization is not that uncommon. So the area that I'm talking about today, as I said before, is the Sunda-Sahul Biotic Interchange. It is an interesting area, not just because of Alfred Russel Wallace's interests, but also because it has a very dynamic geological history. Now we see here the movement of Australia towards the northern part, and it slowly meets up with the Southeast Asian area. But what's interesting is, of course, so it's made up of two main continental masses that we know as Sunda, which is the southeastern part of Asia, and then Sahul, which is New Guinea, the island of New Guinea, as well as Australia. Now what's interesting is these two continental land masses have never, up till now, been connected by dry land. What we have instead are a series of islands in between as also around the area. So there's the transition zone of Wallacea that Octavio alluded to earlier, but also the islands towards the east of New Guinea. We have the East Melanesian island like Fiji, Vanuatu, Solomons. So there's a lot of these islands around the area, and rather than a direct land bridge, of course, we have these islands. And then, of course, yes, we had Wallace's line that explains sort of the separation between the uniqueness of the biota, where fauna to the left of the line is more Asiatic, and to the east of the line more Sahulian. And this area is home to many, many, many different interesting birds, whether phenotypically, environmentally, just by pasturines alone. There's so many different species that, it's hard to collect data on them and span so many different countries. So as part of my last chapter, one of the aims is to use ancestral state estimation methods to investigate how dispersals and diversification change over time. Specifically in this talk, I won't be talking about everything in my last chapter. I'll only be talking about three main sort of topics: sources and sinks through time in the area, dispersal pathways, as well as a little bit of the upstream colonization that I talked about earlier. So to do this, you only need two very simple things that you need an entire PhD to do. First of all, you need a phylogenetic tree of the species you're interested in. And second of all, you need presence-absence data of all the species. Very, very simple. This has to match, and that's basically what I did throughout I don't know how many years. So first of all, I have a phylogenetic tree. So this is a sort of new phylogenetic tree I made. It contains all the pasturines, specifically in the Indo-Australian region. So I combined this with presence-absence of these species in the area. I categorized this into 10 separate areas, as you can see in the map. So from Southeast Asia towards Australia, and also separating it sort of per island groups. For the sake of this presentation, I would sometimes just group them up as three main groups, which is Sunda, the continental mass of Sunda for the west coast area, Sahul, the Wallacea, and also East Melanesia. This is just to simplify some explanations. So when you have these two things, we can then do the main analyses, which is very similar to what Octavio did, because we talk about things together. And that is using ancestral state estimations using biogeobears. So after conducting, running the different models, so for my analyses, I used the DECJ model that we all know and love. I also ran some stochastic maps, similar to Octavio, and identified for this talk, I'm only using 2 different events that we identify. The first is founder events or jump dispersal events, where the daughter lineage occupies a new space than the ancestral lineage, as well as range expansion events. So this is when the daughter lineage occupies a new event, but still occupies the old event as well, so range expansion. And these 2 are what I consider both as dispersals. Yeah, so I will be talking about some of the results of this dispersal. So when I identify events in the tree that dispersals occur, I can then collate the information on which areas through time and space were sources and which are sinks, as well as the dispersal pathways through time. So I will show you. So again, this will be grouped up to the big 4 categories as earlier. I'll be showing you a graph of net migration in a second. So net migration has a very different color from the screen. But anything above 0, so there's a line in the middle, which is the 0 line. Anything above 0 means they're positive net migration, which means they're a source of migration from somewhere to somewhere else. And if they're negative, that means they're sinks, so they're receiving lineages. So here we can see that Sahul, which is Australia and New Guinea, also known as the origin of songbirds, so it makes sense that they've been a source over time. As you can see, it's always above the 0 line. Sunda, on the other hand, which is the Sunda or the Southeast Asia continental shelf, has only recently turned into a source after the last 30 million years. So that's when they first gotten the influx of passerine lineages from Sahul. On the other hand, the islands of Wallacea and East Melanesia have mostly been sinks. So as expected, they've been mostly receiving lineages from other sources. Although we can see the East Melanesian line in particular is quite interesting because in the last 1 to 2 million years, it's sort of getting an uptick of new species, it seems. So that's the for sources and sinks. So this is sort of an average over time. We can also look into this in more detail, so looking at the dispersal pathways in particular. Also, if I actually ran the analyses on the whole crown tree of the passerine, which is around 50 to 60 million years, but nothing really happened in the very old 40 million years and older, which is why I'm only showing sort of the 35 to 30 million years as the oldest part here, because that's where the exciting things happen. So when we look at dispersal pathways, I think I pressed back. There you go. Next. So here you can see in around the 30, 35 million years, nothing much really happened. It's quite boring at that time. There's nothing. The birds are just moving. There's not a lot of them. Also, the size of the circles shows the size of the landmass during that period of time. So here you can see it's mostly just Australian birds going to New Guinea and Sunda birds going to, I don't even know what that is, Borneo probably. And then you can see slowly as we go, more to the current time, nothing much happening. And here you can see the first instance of the dispersal between New Guinea and Asia. So this is when you can actually see the lineages in Asia starting to grow and dispersing to other regions within Asia. So this is sort of when we sort of detect the first New Guinea to Asia dispersal. This is followed by even more dispersals over time. And what's interesting is you can see that towards the older part of in the olden days, so more towards the left side, you can see most of the dispersals usually occur within the shelf, so within the Sahul shelf or within the Sunda shelf itself. But when you see in the 10, 15 million years, you're starting to see that rather than direct dispersals from Sunda to Sahul, you're actually getting the islands as a mediator for dispersals in between. So to get from Sahul to Sunda, they go through the islands rather than going to direct pathways. So this is more, you can see it even more in the 5 to 10. So most of the dispersals are also biased to the more current time, because that's due to our ability to detect it in the methods, because we use current distribution data. So to conclude the dispersal pathways, basically the islands, especially in the more current time periods, are facilitating dispersal between the Sunda-Sahul biotic interchange. We can sort of average this over time, and it's basically just looks like everything is connected to each other. And that's just because it's averaged over time. And although a lot of the dispersals occur in the present time, overall, it looks like everyone, birds just move everywhere, basically, except for directly between Australia and Asia, which I guess is a really long flight, as we know. Another thing that I also included in this talk is upstream colonization. So you could identify nodes in the tree where colonization occurred from islands to continents. This is sort of me trying to plot the number of agreeing maps, which means that we're sort of more confident when it's a high, like a lot of the stochastic map seems to agree that there's upstream colonization, and we can identify some interesting groups for some people who likes birds. For example, we seem to have confidence that honey eaters and flycatchers seems to have gone some sort of island to continent dispersals. Somewhat less confident for birds such as the pitas and cuckoo shrikes. And then we have a little bit less confidence for things that occur even deeper in the node because we have less confidence in deep history events. So these are the estrildid finches and the white eyes. So just gonna conclude. I'm just showing the differences in how sources and sinks change over time and how some areas change in roles through time. Dispersal pathways also change through time, as well as the importance of island, not just as sort of stepping stones for dispersals between the areas, but also as potentially important sources for several bird radiation. And for that, thank you everyone, and thank you for the people in the lab or some of them are here, and I would just like to say I'd really like to talk to people who are very interested in the area, or are from the area, or working with the area, or working on the area, and I'm technically unemployed. So, and with that, thank you very much.
There's time for a question, if anyone has one.
Is there anything known about the fossil record of like any of these birds, or anything that might like help corroborate like exact pathways that you found here?
So there are bird fossils. So part of the phylogenetic tree included some passerine calibrations, but whether or in some of the islands, it's really hard to find fossil. I mean, it's really hard to get genetic data on some of these island endemics. So it's even harder to get fossil data for some specific areas. So it's still a work in progress. And I think it's a good mutualism between the geologists and the biologists trying to figure out what the hell is happening in this area because it's just so dynamic. So yes and no.
Thanks, Audrey.
So as Alex said, my name is Kat Magoulick. I'm a PhD candidate at UC Berkeley, studying with Charles Marshall, and today I'm going to be talking about the Great American Biotic Interchange. There we go. So thankfully, Katherine gave a really great intro into Gavi, but just a little bit of summary points. So it happens when the Isthmus of Panama connects North and South America, and we see this interchange across lots and lots of taxa. In this case, today I'm going to be focusing on mammals. And for mammals, this interchange accelerates about 2.5 million years ago. We see about twice the number of groups migrating south versus north, but in terms of the overall source pools, it is relatively symmetrical. And then North American taxa that end up in South America tend to diversify more, as Katherine just talked about. And I really first became interested in this topic when reading the 1950 paper by George Gaylord Simpson, and I came across this figure that he has in there. And he lists all the taxa that are going north versus south, and notes that to varying degrees, things are getting stopped when they're trying to go to the opposite continent. And he postulates the idea of what he calls the Central American filter. He doesn't really note what he thinks causes it, other than it's probably ecological in nature. And he proposes like various different barriers in this area. So you can see an old barrier zone, a filter zone, and various parts that he has divided it up into. And then he goes on to list the taxa that are either staying on their continent of origin or going to the other continent. So these include groups like the only North American marsupial, the opossum, going from South America to North America. Giant ground sloths, armadillos are all going north, and then things like camelids, felids, and canids go south. So this really brought up the question for me, why are some of these groups migrating but others aren't? And first, let's get ourselves situated in terms of what's going on ecologically during this time period. So within the last 6 million years, there's the trend of global cooling, as you can see here. And then we also get the onset of northern hemisphere glaciation, which you can see in these big spikes and dips over here. And then, as Juan's question helpfully just brought up, it's been postulated that this is leading to a spread of savannas during the glacial periods, and that we're contracting on the rainforest in South America, as you can see here in the green, and that this could possibly be leading to more savanna-adapted genera and generalists to migrate into South America. Although I do want to note, this is from S.D. Webb's paper in 1991, and to my knowledge, this is not based on any sort of global climate model, but rather just his knowledge of the fossil record. So what are the possible migration routes that these groups could have taken? We'll take the perspective of a group going from South America to North America. So they could take the low road around the Amazon. They could take the high road through the Andes, and then these meet in the middle to go through Central America and spread up what into now is the United States. Alternatively, you could stick to what's known as the Gulf Coast corridor. And then, as Audrey points out, you actually don't really need a land bridge at all. You can go across islands, so it's possible that some things were actually potentially rafting throughout the Caribbean. So we get this differential migration. Can we predict this with niche modeling, which is what I'm going to be talking about today? So in order to make a niche model, you need some sort of environmental data, and in this case, we're getting that from the general circulation model created by the group at Bristol. And the 3 parameters we're using here are the precipitation of the wettest month, precipitation of driest month, and the minimum temperature of the coldest month. Then we can put that into our niche model, and we also need some occurrence data. So in my case, I got that occurrence data from GBIF, the PBDB, as well as a literature search. This data here is just simulated data. It doesn't represent any actual real species. But once we have that occurrence data, we can overlap it with our environmental layers and then put it through our algorithm, in my case, maximum entropy, and we get a niche model in ecological space. We tend to use the terms ecological niche modeling and species distribution modeling interchangeably, but they're actually a little bit separate things. We're thinking about the niche and ecological space here, and then we can also project that back into geographic space for our species distribution model. And then here's just what a simulated distribution model would look like, in this case indicating habitat suitability in pink. So if we can measure our habitat suitability, then we can sort of start to assess these migration hypotheses. And this niche modeling work has really been in conjunction with Aaron Staup at Oxford, who is an expert in utilizing fossil data for niche modeling. So given the suitable habitat, we expect migrators are going to have more of that, especially in Central America, but is this going to be the case? So like many others in this symposium today, I had grand plans when I started my PhD to do this across all mammalian taxa. Turns out that's really quite time consuming, so today we're just gonna focus on one, Glyptotherium. They are a relative of armadillos, quite large, weigh a couple tons, just a little bit smaller than a Volkswagen Beetle. And they are originally from South America, we think, based on phylogenetic relationships, but we see their first fossil occurrence about 4 million years ago in Mexico. And one of the reasons I chose this group is because they have these really distinct osteoderms, which you can see over here on the left. which allow us to get a good taxonomic ID to genus and species. And they're also quite numerous because, as you can see, they're making up this whole shell here. So where was Glyptotherium living? Well, based on our savanna hypotheses, we wanted to test something that was adapted to savannas. So they're a generalist grazer living in a savanna with some open trees. And then once I had the data from GBIF and PBDB in the literature, I realized that I need to refine it even more temporally, rather than just focusing on these North American land mammal ages, which, as you can see here, can span across millions of years. I wanted to constrain it to try and get more of a sense of animals that were living approximately at the same time. And here you can see that we have this concentration here in the Rancho La Brea, which I think is just a byproduct of being able to radiocarbon date things within the last 50,000 years. And the Rancho La Brea spans the last 250,000 years. So unfortunately, this means we don't have enough data from the interchange acceleration, but we can use hindcasting of our models to get back to that time period, which is what I'll show you in a bit. So here are all those about 200 localities across all time periods. And then focusing on the green dots for the Rancho La Brea, we're able to spatially filter them, and we end up with about 25 localities. Then we can take these localities and put them into our max-end model. This is what I look like when I'm coding. And it was quite interesting. So I was thinking a little bit about the ecology of Glyptotherium in general. And in the 80s, it was postulated by paleoecologists that they would have needed a relatively warm, wet environment. And this is actually confirmed or supported by our model. So within our environmental variables, across all of our runs, the most important variable was always the coldest month minimum temperature, which likely indicates that that's what's constraining the range the most of these animals. So it supports that they probably did need a warm environment. So then looking at our maps, here is the habitat suitability based on our model. So anything in the yellow is going to be indicated as high suitability for the model, and anything in the purple is going to be low suitability. And then what we can do is, based on different measures, we can take a point on here to create a threshold and say anything below that threshold is going to be an absence for Glyptotherium, anything above will be a presence. So here in blue, we do that for the Rancho La Brea, and we see that there is definitely some connected habitat, as we would expect in Central America. But if we go back further, again, to around the peak of the interchange, the acceleration of the interchange about 2 million years ago, we see drastically more and more connected area in Central and South America, which is what we're expecting. And these two are just different ways of thresholding the model, one slightly more conservative here on the right. And then finally, we can go back even further before the acceleration of the interchange and see what it looks like. We see relatively similar, again, a lot of habitat that is suitable here in Central America. But you can just say, oh, well, that's just visual. How are you actually quantifying this? So we're using fragmentation statistics here. And this is actually something that's been used a lot more for extant niche models, but I think it's a really valuable tool that we should apply more to our paleo ENMs. So we're using percentage of suitable conditions and AI, but not the one you're thinking of. Here it's aggregation index. You can see this square up here would have an aggregation index of 0. All the pixels are far apart and not touching. But down here, we would have an aggregation index of 100 because all the pixels are clustered. So it's measuring not only whether the pixels are touching, but how clustered they are together. So looking at these two statistics, it's a lot of numbers here, but you'll see that I've bolded the highest number in each column. So we're seeing that in the late Blancan, about 2 million years ago, we're seeing the most connected habitat, which is generally what we expect given Glyptotherium's expansion during this time, as well as the savanna hypothesis. But it becomes a little bit less clear when we're looking in the middle Blancan. So I've chosen to compare some of the migration routes. So we have the low road and high road, which are over here in these two columns on the right. And it's less clear depending on which threshold we look at where there would be more suitable habitat. And I'm actually trying at this moment to hindcast the model back even further to about 5 million years ago, so we can see before our first occurrence of Glyptotherium 4 million years ago, and what those different corridors might look like then. So our conclusions for Glyptotherium is that overall, we do see suitable habitat through Central America, which could act as a corridor for their dispersal, indicating that, at least in the case of dispersers during Gabi, niche models are a tool that we can use to assess that. And they also support the hypothesis that Glyptotherium is needing a warm, wet environment. Now, I also want to look at non-migrators. Unfortunately, I don't have the beautiful maps for them yet. But again, going back to that hypothesis of savanna expansion, I wanted to look at groups that are both savanna adapted and not savanna adapted. So 2 groups that don't migrate and stay here in North America are the beaver, which goes around here as its lowest point, and then the pronghorn, which gets further into Central America as its lowest point. But I'm particularly interested in the pronghorn because I think would expect them to migrate based on the savanna adaptation hypothesis, but we don't actually see that. So I'm interested to see what the models there will say. I'd really like to thank Alex and Octavio for organizing this symposium. It's been great to chat with everyone about biotic interchanges. I'd also like to thank everyone who's helped me along the way in this research and my funding sources. Also, I am currently finishing my PhD and looking for postdocs, so if you have any leads on that, I'd love to chat. And more generally, I'd love to chat about niche modeling, the fossil record, and biogeographic patterns. With that, I'll take any questions.